So welcome to the lecture on vibration absorber. So today we will discuss the theory of undamped vibration absorber. So what is a vibration absorber? As from the name we can understand that it absorbs the vibration. So it means there is some system that is in vibration. So it could be in vibration due to some external load, and vibration absorber is another system that if we attach to the main system, the vibration of the main system should reduce. So if we have a main system and we can model it as a single degree of freedom system, and the vibration absorber is also a dynamic system and it can be modeled as a single degree of freedom system, then the total system will be 2 degree of freedom system. So the vibration absorbers, they are used in several applications where there is vibrations and the system is running at a constant speed. So like reciprocating engine that are designed for running at constant speed with minimum fuel consumption. So these systems, they can work in a very narrow band of frequency range because they are tuned for certain frequency range, and therefore we will also call them the tuned vibration absorber when they are tuned for certain frequency. So here second example is the transmission lines. So we can see here the transmission lines, there are the cables and they are passing and due to the wind they get excitations and they can vibrate. So to reduce the vibrations, we can see that here we attach a vibration absorber, that is a dumbbell shaped device, and this can mitigate the vibration due to the wind excitations. So any machine or any system that is subjected to some harmonic force, okay, and it is because we have already seen that when a system is subjected to any harmonic force, it will start vibrate and the steady state vibrations will be governed by the harmonic force that is acting on the system. So if we want to reduce the vibrations, we have to design a vibration absorber and we have to attach this to that system, and this vibration absorber will be have capability to reduce the vibration. It will shift the resonance frequency. So we will consider the 2 degree of freedom system. So this is our 2 degree of freedom system. So here we can see, here is a machine and that is resting on some springs and on the rigid base, and this machine is subjected to some unbalanced forces, maybe F0 sin omega t, that is acting on the machine, and due to these forces the machine will have steady state vibrations. And so if we want to reduce these vibrations, we have to attach another system, we can see here. So the main system is here, the main system is represented by the mass m1 and stiffness k1, because here there are 2 springs, k1 by 2 and k1 by 2 stiffness. So the total stiffness, because they are in parallel, will be k1. So the main system is represented by a mass m1 and spring constant k1, while the absorber system is represented by mass m2 and stiffness k2, and this system is attached to the main mass. So this system can be represented in this way. So we have a spring k1, then mass, main mass, that is m1, and then spring k2, that is the stiffness of the absorber, and the mass of the absorber. So we have this system. So we can write the equations, and we can find that we have to derive that how the response of the main system is being affected or it is being reduced due to the introduction of the secondary system, that is the vibration absorber. So this is our K1 M1, K2 M2. So K1 M1 is the main system and K2 M2 is the absorber system, and this is attached to the main system. Now this main system is subjected to some harmonic force, that is F0 sine omega t, and this is the response x1 of the main system, and this is the response of the absorber, that is x2. So now we can write the equations. So we have to make the free body diagram of the masses and show the forces. Then we have to apply the Newton's second law to write the equations of motion. So here we have m1. So this mass, when it is pulling this direction, so we assume this direction positive, so it is going to stress, so the spring force is working in opposite direction, that is k1 times x1. Now we assume here x2 is greater than x1, so the net force acting on the mass is in this direction, that is due to the spring k2, that is k2 x2 minus x1, and there is the harmonic force acting on this system, so that is F0 sine omega t. Now the second mass m2, so m2 will have the same force k2 x2 minus x1 in opposite direction of that of the mass m1, and no any other force, and the direction of acceleration we assume this as a positive. Now we can write the equations of motion. So we have for the first mass m1 x1 double dot equal to summation of the forces, so minus k1 x1 and plus k2 x2 minus x1 and plus f0 sine omega t. So here we can write m1 x1 double dot plus k1 plus k2 x1 minus k2 x2 equal to f0 sine omega t. Now for the second mass, so let's say this is equation number 1, then the second mass we write m2 x2 double dot equal to minus k2 x2 minus x1. So we can rewrite like m2 x2 double dot plus k2 x2 minus k2 x1 equal to 0. This is equation 2. Now, as we have already discussed in the 2 degree of freedom systems, that the complete system will vibrate with one frequency at one time, and that will be its natural frequency. And this is the 2 degree of freedom system, so it will have 2 natural frequencies. So the 2 frequencies and 2 natural frequencies and 2 mode shapes corresponding to each frequency. So here we assume that the system is vibrating with frequency omega, the same frequency as the forced frequency, because the steady state response of the system will be governed by the external excitation force, that is F0 sin omega t. So we assume that x1 equal to x1 sin omega t and x2 equal to x2 sin omega t. Now we can put these values here in these equation 1 and 2. So x1 is x1 sin omega t, so it means x1 dot is x1 omega cos omega t, and so x1 double dot equal to omega square minus x1 sin omega t. So minus omega square x1 sin omega 2. Similarly, x2 double dot equal to minus omega square x2 sin omega t. So now we put this x1 double dot value here in equation 1 and x2 double dot value here, and x1 value here and here, and x2 value here and here. So what do we get? So here if we put, so minus m1 omega square x1 plus k1 plus k2 x1. Of course here will be sin omega t and here also sin omega t minus k2 x2 sin omega t, that is equal to f0 sin omega t. So we can cancel out sin omega t, or we just take this part. So minus m1 omega square plus k1 plus k2 x1 minus k2 x2 equal to f0. This is equation number 3. Similarly, we can have equation 2. So minus m2 omega square x2 sin omega t plus k2 x2 sin omega t minus k2 x1 sin omega t equal to 0. Again we can write here minus k2 x1 plus this is K2 so we have minus m2 omega square plus K2 x2 equal to 0. So this is equation 4. So we have now these two equations, equation 3 and 4. So from here we can find x2 equal to minus K2 x1. So it will be plus, so if we take this other side, so K2 x1 by minus m2 omega square plus K2. Now we put the value of x2 in equation number 3 here. So we have minus m1 omega square plus K1 plus K2 x1 minus K2 into x2. So here x2 is K2 x1 by minus m2 omega square plus K2, and that is equal to f0. Okay, so we can solve this equation for x1. So So if we solve for x1, we will have minus m1 omega square plus K1 plus K2 into minus m2 omega square plus K2. Because this term will multiply this term, minus K2 square equal to f0 into, so this term will multiply here and here, so it is K2 minus m2 omega square, and here we can write x1 because x1 is common here and here, so it can go in the denominator. So we can solve this. So that is m1 m2 omega power 4, and then it is minus m1 K2 omega square, and this is plus K1, so it is here minus K1 plus K2 m2 omega square plus K1 K2 plus K2 square minus K2 square, and that is equal to f0 by x1 K2 minus m2 omega square. So now this K2 square will cancel out, and we can rewrite this term. So m1 m2 omega power 4 minus m1 K2 plus m2 k1 plus k2 omega square plus k1 k2. So that is equal to this term. So we can write x1. So x1 is equal to f0 k2 minus m2 omega square upon m1 m2 omega power 4 minus m1 k2 plus m2 k1 plus k2 omega square plus k1 k2. Okay, so we have got the x1. We have got x1. Now we put the value of x1 here and we will get x2. So x2 equal to, we put the value of x1. So we put the value of x1 here. So here in denominator is k2 minus m2 omega square, and in the numerator here is k2 minus m2 omega square. So they will cancel out, and we will get f0 k2 upon m1 m2 omega power 4 minus m1 k2 plus m2 k1 plus k2 omega square plus k1 k2. So this is what we have got. Okay, so we have got x1 and x2. Now we can rewrite these equations as, because here we have omega 1 is the natural frequency of the first system. So that is root k1 by m1, and omega 2 is the natural frequency of the second system, that is root k2 by m2, and we define mass ratio, a term mass ratio, that is mu, and it is m2 by m1. So mu is defined as the ratio of the two masses, that is the mass of the absorber and divided by the mass of the main system, that is m2 by m1. Now we define one more term, x st So x st is defined as the zero frequency deflection of the main system due to the force F0, that is the zero frequency deflection. Now we can rewrite these x1 and x2 in terms of these parameters. So we can write here, so x1 so we can take k2 outside here. So this equation we can convert like f0 k2 minus m2 omega square. We can do like f0 by k1 into k1 into k2 1 minus m2 by k2 omega square. So here f0 by K1 is x st into K1 K2 into 1 minus. So here K2 by M2 under root is omega 2 square. So we can write omega square by omega 2 square. And this K1 K2 term, because this will come in the numerator, we can take here and we can divide here. So we can write, and we take this xt term to other side. So we will write x1 by x st equal to 1 minus omega square by omega 2 square, and K1 K2 will divide these denominator terms. So this is omega power 4, and if we divide, this will be by K1 by K1 K2. So they will be K1 by M1 is omega 1 square and K2 by M2 is omega 2 square. So we will have omega 1 square and omega 2 square minus, here we will again K1 by K2. So K2 will cancel out, we will have M1 by K1. So we can write 1 by omega 1 square. Here again we will have M2. So here M2 K1 by K1 K2. So M2 by K2. So it is 1 by omega 2 square, and this is K2 M2 by K1 K2. So it is K2 M2 by K1 K2. So we can cancel out here this K2, and we divide it and multiply with M1 by M2. So what will happen? These terms we can write so this is M2 and M2 K2 here by K1 K2. So we will have here M2 by M1, that is mu, M2 by M1 is mu, this term M2 by M1, and K1 by M1 is omega 1 square, and this term is multiplied by omega square, and then this is K1 by K2 by K1 by K2. So it is 1. So here we can have this equation again modified. So we will have so x1 by x st equal to 1 minus omega square by omega 2 square upon omega 4 by omega 1 square omega 2 square minus omega square by omega 2 square plus 1 plus mu omega square by omega 1 square plus 1. So this is x1 by xt. Similarly, we can write x2 in this form. So if we write f2, so f0 k2 we can write like f0 by k1 into k1 k2. So f0 by k1 is x st, and k1 k2 we can divide the denominator terms. So we will have the same denominator term, but because x st will go, we write x2 by x st. So in the numerator there will be 1. So we can write x2 here. So we can write x2 equal to 1. So x2 by xst equal to 1 upon omega 4 by omega 1 square omega 2 square minus omega square by omega 2 square plus 1 plus mu omega square by omega 1 square So we can see that this is the response amplitude of the first mass, the main system. So x1 is 0 when omega is equal to omega 2. When omega is equal to omega 2, so it means that the natural frequency of the absorber is equal to the excitation frequency. We will get the zero response of the main system. So therefore if we select, because omega 2 is root k2 by m2, so if we can select k2 and m2 such that the under root of k2 by m2 is equal to the excitation frequency, then the main system will have zero vibration. So it zero amplitude vibration. So it will be at still, it will stop. So vibration will be mitigated of the main system. So now I would like to stop here and see you in the next lecture. Thank you.